the conclusion was altered considerably from the previous version, and they thanked Professor Robertson for his clarification. And nowadays, we know actually that an anonymous referee was indeed Robertson. Okay, so actually the Bondi-Sachs formalism appeared in the 60s as a solution to many of those questions. In particular, it showed in a nonlinear way that gravitational waves carry positive energy, and also clarified and characterized the gauge dependency of the gravitational field. So there are two main ingredients of the Bondi-Sachs formalism. One is the choice of Bondi gauge. So this is a coordinate system which is adapted to null cones. So this is very important because, for example, because it removes some log divergences that appear in other coordinate systems such as the harmonic coordinates. So in harmonic coordinates, what happens is that, okay, linearized solutions propagate along coordinate cones t minus r equals constant. But when you consider the back reaction of the source and the wave, you see that there is a logarithmic deviation between the coordinate cones and the physical light cones defined by the congruence of the gravitational, the null rays. But in Bondi gauge, by definition, the coordinate cones coincide with the null cone, the physical geometrical null cones. And this is very important. The next point of the Bondi-Sachs formalism is the asymptotic analysis of Einstein equations. So what it means is that you assume that you have a localized source of gravitational wave, and you assume that the observer is so far from the source, so that you can expand the gravitational field in powers of 1 over r and solve the Einstein equations order by order in 1 over r. So let me give a bit more details, although Celine told us about this, though in 3 dimensions. So in 4 dimensions, you have u, r, and theta a. So u is the retarded time and is defined as a light coordinate. R is the radial coordinate, which is defined to be the areal distance. So a sphere, coordinate sphere has always area 4 pi r squared. And the thetas, the angles, are defined to be constant along outgoing null rays. So you can show that these 3 conditions are equivalent to these famous Bondi gauge conditions. And then when you pose these conditions, the metric takes this form. And as you notice here, in the metric, there remains only 4 objects to be determined. 2 scalars, beta and u, 1 vector in the sphere, ua, and a metric GAB in the sphere. Please interrupt me if there is any question. So the next step is the asymptotic expansion. So you take these 4 objects and expand it in powers of 1 over r, as I mentioned. So the leading term is typically refers to the Minkowski background, but the more physical quantities appear in the next order. So here we have CAB, which is called the Bondi shear, and it contains the information about the transverse traceless part of the gravitational field, which is the gravitational wave. And then we also have M and NA, which are the Bondi mass and angular momentum aspects, which contain the information about the total energy and angular momentum of the system. Okay, let me mention a point about boundary conditions. So Bondi and Sachs imposed as a boundary condition that this gamma AB, the leading metric on the sphere, is just the round metric. But one can actually relax this condition, and this was mentioned in Barnett and Trossard. So you can, if you define asymptotically flat spacetime in the sense of Penrose simplicity conditions, you can allow for arbitrary metric on the sphere, and even it can have U dependence. For the purpose of this talk, I will drop this U dependence, but otherwise consider this gamma IB as a general metric. Okay, the next step is to solve the Einstein equations. So when you do this order by order in power of 1 over R, the first thing that you notice is that gamma AB and CAB are free data. So there is no constraint from the Einstein equations on these quantities. So gamma AB and CAB are these guys here. Then you have a set of algebraic equations which determine some of the coefficients in your asymptotic expansion in terms of the free data, as you see, for example, in these equations. Apart from those, you have a set of what I call balance equations. The most important of them are the balance equation for mass and angular momentum aspect. And what they do is to give the time evolution of the Bondi mass aspect and angular momentum aspect in terms of fluxes of in terms of the free data. So you notice here that you have quadratic terms in the shear and also linear terms in the shear. You can call this hard and soft if you want. Okay, is there any question so far? Okay, now the BMS symmetries. So BMS symmetries are by definition those diffeomorphisms that preserve the Bondi gauge as well as the boundary conditions. And in this case, I take the relaxed boundary conditions I mentioned. So what you find is this, the so-called generalized or extended BMS symmetries, which contain the supertranslations and the super Lorentz transformations. The supertranslations are actually angle dependent time translations, while the super Lorentz are some arbitrary deformations on the sphere, on the celestial sphere, that is combined with some suitable scaling of time and radius. Okay, sorry. So I should make a remark here. So Barnett and Trossard, so here you have these parameters t and y for the transformations, for the symmetries. Barnett and Trossard used the holomorphic basis to expand these gauge parameters. And this is usually called extended BMS, so that you get 2 copies of Virasoro and so on. But what is usually called generalized BMS is the case that you take these functions to be smooth on the sphere, so you can expand in spherical harmonics. And this is what I focus on in this talk. Furthermore, you can expand this vector y, the generator of super Lorentz, in terms of 2 scalars on the sphere using the inverse Levi-Civita and the metric. And then you expand this in your BMS generator. You see that the super Lorentz bars breaks into super rotations and super boosts. And why I call them like this? The reason is that if you now expand these 3 functions in a spherical harmonics, you see that the standard, the Poincaré algebra is just L equals 0 and L equals 1 in this expansion. And the higher ones are called super. Okay. Now let's talk about the charges associated to these symmetries. Well, there is a long story as we heard in the nice talks before. about integrability and so on, but I skipped those issues. And but the final result, which resembles a lot to the result showed by Celine, is this one. So you have the super momenta corresponding to the super translations as the integral of the Bondi mass aspect with a VLM. And similarly for super angular momentum and super center of mass corresponding to super rotations and super boosts. And these two are constructed out of the angular momentum aspect multiplied naturally with a vector spherical harmonic. And these are the two vector spherical harmonics. So these charges, if you want, are the Noether charges associated to BMS symmetries. Mm. But as you see here, clearly, these charges, these surface integrals are not conserved quantities. Instead, they obey some certain balance equations, and this is what I want to focus on in this section. So the balance equations for the BMS charges can be derived from the definition of the charges combined with the Einstein equations. So I start, for example, for super momentum, I start with the definition here. And then I take a time derivative on both sides, and I use the Einstein equation for the time evolution of the mass aspect, and I derive this equation. So this is the balanced equation for super momentum. You can do similarly for super angular momentum and super center of mass, although the result is a bit more complicated. But you may wonder, what is the importance of these equations? I mean, who cares about these equations? As I said, my motivation is gravitational waves. So the thing is that if you can relate the BMS charges to the source of gravitational wave in a way, then this equation becomes non-trivial because it tells you how the source will evolve in time in terms of the radiation that you observe at scribe plus. Okay, and I will come back to a concrete example of this later on in my talk. But in order to connect to the source, and actually it is very standard in the analysis of gravitational waves, to expand the gravitational wave in terms of the so-called radiative multiple moments, U and V, and these are called the mass and the spin multiple moments. So you see a lot of indices here. So this refers, these are actually another version of the spherical harmonics where you take these ni's defined as xi Cartesian xi over r, and then you multiply L couple of them, and then take the trace-free part. So this is called the STF spherical harmonics. So when you have L indices like here, this is a spherical harmonic of rank L. So this is, it turns out this is very useful for practical computations. I mean, you can compute everything just by combinatorics of these NIs. Okay, so you can put this expansion in the previous equation for the BMS flux balance equations and obtain the balance equations in terms of the radiative multiples. Let us first focus on the Poincaré subset of BMS balance equations. The Poincaré subset corresponds to the flux balance equations for energy, angular momentum, linear momentum, and center of mass. And the fluxes are given by these expressions. So although it might look a bit complicated, but everything is clear. I mean, all the coefficients are well defined, just combinatorics. And you see that the fluxes are quadratic expressions in terms of the radiative multiples everywhere. Okay, actually this result matches with the results of other groups from actually other viewpoints, not starting from Bondi gauge. And then, okay, the next step is that you can relate these fluxes, I mean, these radiative multiples to the source multiples. I mean, if you want to write down these asymptotic data in terms of the source, you should relate the radiative multiple moments to the source multiple moments. And this is a known result in the post-Newtonian literature. This is not an exact equation, but there is some approximation, but you can do more. You can compute higher orders if you want. But when we put this in our previous flux balance equations, we get these results. And this result matches exactly with several different results in the literature obtained over the years by starting from Einstein. This is the Einstein quadrupole formula, the famous one. And then the other results were derived by Thorne and others later on. But this is very interesting that from this perspective, you can find all of them in a very coherent manner. Okay, so here is the concrete example I wanted to mention. So this is an application of the flux balance equations for a radiating system, which is a binary system. So consider a two-body problem on a quasi-circular orbit, meaning that the two objects are orbiting on a circle whose radius shrinks very slowly with time. Then I write down my flux balance equation for energy. This is what I showed you before. And then the next point is to relate, as I mentioned, is to relate the BMS charge, which is in this case the energy, to the source. And I do this in a very intuitive way. So I take the energy to be the mechanical energy of the system, composed of the kinetic and potential energies, and it's given by this Newtonian expression. So this is the left-hand side. And the right-hand side, the mass quadrupole moments are also known in terms of the source. So you can also write the right-hand side in terms of the parameters of the source, namely the radius of the object and the angles and so on. And then you can solve this first order differential equation to, I mean, solving this equation completely it solves the evolution of this system. So you can find exactly the orbit, the radius of the system in time. I mean, to this order of precision in time, and then you can also accordingly find the waveform that is generated by this system, and you see that this is already some approximation of what we see in LIGO. So this is a concrete example of using balance equations for radiating systems.
So Ali, there are only a couple of minutes left. See if we have want to have time for questions.
Okay, so you can do similarly for higher BMS balance equations. For example, for supermomenta, it took like this expression. It's a bit long, but everything is determined here. Here you have also soft terms and hard terms. For Poincaré, you only had quadratic terms, hard terms, but here you have also linear terms. Then you have parity, odd, and even terms, which are given here, and so on. And similarly for other BMS equations, just some examples here. truncated to some order. This is, for example, the balance equation for super angular momentum at L equal 3. So these are some examples. So as I said, the critical point is to relate the BMS charges to the source. And for Poincare charges, we know how to do this. We take the, we use our physical intuition to do that. But for higher BMS charges, we still don't know how to relate the asymptotic expression to the source. And this is the remaining part of this project. So I don't know how much time I have.
Well, so there are 5 minutes left, but we probably need some time.
I wanted to quickly mention about memory effects. So let me quickly go through this and then maybe a few minutes for questions. So to relate to memory effects, it's better to even start from the Einstein equation itself. This is what I showed you before. And then you integrate over time. So by these brackets, I mean the difference between the final time and the initial time. So you get, after integration over time, you get this. Then on the right-hand side, you have this linear term, the soft term. You expand CAB in terms of two scalar functions, C plus and C minus. Inserting this into the equation, you find that this equation becomes an equation for C plus. This is a fourth order, I mean, these deltas are Laplacians on the sphere. And you can invert this operator, this fourth order operator, to find C plus. And then from this, you can derive the displacement memory, which is the permanent deviation of the test objects, for example, in LIGO. And this can be interpreted as a transition in the vacuum due to a super translation, because under super translation, C plus gets shifted. And you can similarly, by starting from the other equation, this is the equation for mass aspect, you can start from the equation for angular momentum aspect. And as I think Nichols showed first, that you can derive two other sets of memory effects called the spin and center of mass memory effects. Well, to implement these equations like this one, you also need to know what is the initial and final values of the mass aspect or angular momentum aspect. And in our paper, we also gave expressions for the initial and final mass and angular momentum aspects for a binary system. And these are the results for the final boosted super translated Kerr black hole, which is the final state of a binary a merger system. You can do the same for the initial state in which the two objects are far apart and there is no interaction. Okay, I just want to emphasize that okay, asymptotic analysis or asymptotic structure of a spacetime, which is the subject of this workshop, is very interesting because it gives universal information about the gravitational theory, for example, through the asymptotic symmetries in relation to holography and so on. But to extract more information regarding the specific systems, what we need to do is to relate the asymptotics to the bulk. In other words, relate the far zone to the near zone. And related to this, I would like to advertise this recent paper of us last week. You can take a look. Thank you very much.
Thank you. Just one precision, the spin memory was done by Pasterski, Strominger, and Zibroidov in 2016.
Okay.
So I have a question from Andrea.
Yes, hi. So I have a question about, so you show an example where the Poincare flux equation were sufficient to solve the system, at least to the precision that you gave. So what happens then to the other flux equation? So do you expect them to be zero in this case, identically satisfied, or in general, what kind of example you have in mind of a system in which the BMS flux equations were important? So something like multiple Eiger multiples or...
Yeah, this is a good question. Let me mention some things that we know already. For example, if the system is orbiting in quasi-elliptic orbit, you can use the angular momentum balance equation as well as the energy. And then these two determines the system completely. But I don't know exactly, but if you have, for example, spins, I mean, the objects have a spin, or you have multiple objects, or they have internal structures, maybe you need to, I mean, maybe the BMS balance equations become useful, but this is what you're working on. They are not still.
But so the problem is that in this case, you don't know how to write a BMS flux equation, because you don't know how to relate the BMS charges to a Newtonian expression. Is it correct?
Yeah, the right, so, okay, this is the structure. Okay. As I said, I know the right-hand side. I know the fluxes. And I expanded them for you in terms of radiative multiples and later to source multiples. The problem is not on the right-hand side, it's on the left-hand side. So in the case of Poincaré, you know what is the, if you want, Newtonian expression for the charges, Poincaré charges. But for BMS, still, you don't know what is the, let's say, super momentum in terms of the parameters of the source. If you give me that, then I can put it in my equation and see what comes out.
Okay, thanks.
Is there another question? I don't see. No further questions, so let's thank Ali. So we have now Ankit.
Can you see my screen?
Not yet. Yeah, we can see it. If you can go full screen.
Yes. Is it okay now?
Yes, perfect.
Okay, I would first like to begin by thanking the organizers for inviting me to the conference. And I'm going to talk about super translations in higher dimensions. This is a work that was done like 2 years ago. Okay, so I'm going to begin by giving a brief outline of my talk and then some background, the issue that I'm trying to resolve, its resolution, and a conjecture that is proposed in the paper, and I will end with the conclusions. So I guess all of the participants here know that the asymptotically flat spacetimes have an asymptotic symmetric group, which is known as the BMS group. It contains super translations as an infinite dimensional abelian subgroup. But the similar studies of its higher dimensional analog have concluded that there are no super translations in higher dimensions. There has been, the most recent work on this has been by Holland, Ishibashi, and Wald. But this, the fact that there are no super translations in higher dimensions is inconsistent with the with what we know from the soft theorem asymptotic symmetry correspondence that was initiated by Strominger and later picked up by the collaborators. Because we know that Weinberg's soft graviton theorem holds in arbitrary dimensions. So there should be some asymptotic symmetry associated with the soft graviton theorem. We have been able to resolve this discrepancy by showing that super translations actually do exist in higher even dimensions. And here we only work in linearized gravity and only focus on even dimensions, because the notion of null infinity breaks down in odd dimensions greater than 4. For example, if you try to expand the metric in powers of R, there would be fractional powers. So it's not clear how to define a non-physical metric which has a smooth Weil tensor and so on. So I'll just quickly go through the background for completeness. So asymptotic symmetries are the transformations which act non-trivially on the boundary, but leave the form of the boundary conditions invariant. In this talk, the boundary conditions of interest are those of asymptotically flat spacetimes, and the transformations of interest are supertranslations. Now, what do I mean by asymptotic flatness? Asymptotically flat spacetimes are the spacetimes which approach flat spacetimes at large distances. They're intended to represent isolated systems. And a precise definition of asymptotic flatness involves specifying boundary conditions, or the rate at which metric approaches a flat metric at large distances. There's no unique prescription to specify this rate, but it should be slow enough to allow for physically interesting solutions like gravitational waves and black holes and so on. And it should be fast enough to ensure finiteness of the charges associated with the asymptotic symmetries. Now, around 50 years ago, through the work of Bondi-Sachs and Sachs, they found that the asymptotic symmetric group of asymptotically flat spacetimes is not just Poincare group, which one may naively expect, but there's an infinite dimensional generalization of the group to BMS group. And it is a semi-direct product of supertranslations and Lorentz transformations. Around the same time, supertranslations are just, so here, this is the Penrose diagram of asymptotically flat spacetimes. U is the retarded time, which parameterizes the future null infinity. This blue circle is, I'm representing the future at null infinity by this blue circle. So supertranslations translate each point on this sphere independently. So U goes to U plus an arbitrary function of F. This is how supertranslations act at future null infinity. Now, around the same time, coincidentally, there was a separate direction of work in the gauge and gravity theories. So people found out that there are actually factorization theorems in these gauge and gravity theories. So if you have a scattering amplitude with a soft particle, that is a particle whose energy is going to 0, that factorizes into a scattering amplitude without the soft particle, with the soft factor. This soft factor is divergent in the energy of the soft particle going to 0 limit. And there's a simple pole. And this theorem is true in arbitrary dimensions for gravity and for other gauge theories as well. Now, in the last 7-8 years, soft theorems have been understood as Ward identities associated with the asymptotic symmetries. This has been established for abelian theories, non-abelian theories, and by now there is a conclusive amount of evidence that this correspondence holds. And in 4D gravity especially, the leading soft graviton theorem is the Ward identity associated to supertranslations in 4 dimensions. One expects that the similar correspondence should hold in higher dimensions as well, because there are soft graviton theorems in higher dimensions. But it is not very clear how this works because of the following reason. So, as I already mentioned, it has been argued that there are no supertranslations in higher dimensions. The asymptotic symmetry group of higher dimensional asymptotically flat spacetimes is just Poincare group. And the reason for this is that in 4 dimensions, you cannot get rid of supertranslations without also getting rid of the radiation. So they both come together. But in higher dimensions, you can get rid of supertranslations, but still allow for the gravitational radiation. And if you try to, for example, include the, so there is no motivation to include super translations first of all. And suppose if you try to include the super translations in higher dimensions, then you find that the symplectic potential current and charges are divergent. So people usually, what they did was they just imposed stricter boundary conditions because there was no reason to relax them. Now, if you try to relax the boundary conditions, you'll get infinite charges. So how do we overcome this issue? I'll try to first describe it through this diagram. So here, this is again the Penrose diagram of asymptotically flat spacetimes. These green curves represent the r is equal to constant surfaces. R is the radial coordinate. And now the boundary conditions are usually specified near the future null infinity and past null infinity. We will only focus on future null infinity for simplicity. And so boundary conditions are specified as fall-offs in this radial coordinate. What we do is that we also specify some fall-offs in this retarded time, which parameterizes the future null infinity. So we specify the fall-offs in U at very large values of U, that is near the future of future null infinity and the past of future null infinity, which are called scri plus plus and scri plus minus respectively. So maybe some more details about this. So in Bondi coordinates, the flat spacetime can be written as given in equation 1 for arbitrary dimensions. Here, capital A and capital B are sphere indices, and they run from 1 to d minus 2. Now, the boundary conditions that we impose are the same as the ones that are imposed in 4D asymptotically flat spacetimes. These are exactly the same. And this is just for Bondi gauge, and there's a determinant condition for Bondi gauge. Here, gamma AB is the round metric on SD minus 2. So we don't generalize it to some arbitrary metric, as Ali was mentioning. But if you want to include super rotations and so on, you need to do that. But here we are not concerned with that. Now, the claims made against super translations in higher dimensions use stronger boundary conditions than above. The boundary conditions that we showed allow for super translations, but lead to infinite charges. Let us now parameterize the asymptotically flat spacetimes in higher dimensions as in equation 5. Here, the M, U, and G, A, B are expanded in powers of R. But the most relevant component here for us is the expansion of GAB. So for the linearized gravity, these CABs all become traceless because of the determinant condition. And so CAB minus 1, that is the coefficient of R, is the free radiative data in 4 dimensions. But in 6 dimensions, it is not the free radiative data. Instead, the coefficient of that's the order 1 component is the free radiative data, that is CAB0. And if you go to like 8 dimensions, CAB1 is the free radiative data and so on. Now the super translations are generated by this vector field. Here F is an arbitrary function on the sphere. Yeah, and this is an asymptotic expansion. The effect of this expansion on CAB minus 1 is that it changes it inhomogeneously, and it does not change the other components of CAB at the linearized level. So now the fall-offs in U that we impose are this on the divergence of the radiative data. So we say that it should fall faster than 1 over U, near U is equal to plus infinity and minus infinity. And once you impose these fall-offs, you get a finite charge for super translations. And so this actually, this is just for 6 dimension. I'm just writing here the condition for 6 dimensions, but it has also been done for arbitrary higher dimensions, and it is in the paper. And the soft charge that you get once you impose this condition, which is finite, is in 6 dimensions given by this expression. Now, if you write the Ward identity associated with this soft charge, you get precisely the leading soft graviton theorem in higher even dimensions for 6 dimensions in this particular case. Now, how do we actually interpret these boundary conditions, these U fall-offs? So for this, we have to look at the analysis done by Christodoulou and Kleinerman. So they studied the nonlinear stability of Minkowski spacetime in 4 dimensions. And so in simple terms, what they did was they studied if you start with a small perturbation at some initial time slice, does it continue to be small at a later time or not? And they found some conditions for this to be true. And the spaces which satisfy these conditions are known as Christodoulou-Kleinerman spaces. And this implies some conditions on the radiative data near the boundaries of null infinity, that is at scri ++ and scri ±. And these conditions actually turn out to be essential for having a well-defined scattering problem. And this analysis has not been performed in higher dimensions. So we conjectured that this actually these U fall-offs that we are imposing are nothing but the consequences of Christodoulou-Kleinerman constraints in higher dimensions. So if that analysis is done, then we suspect that it will turn out that these U fall-offs follow. And the reason for this is based on a counting argument. So I can go into the details if people are interested, but that's what we suspect. So I'll end with the conclusions. The focus of this talk was to clarify the connection between supertranslations and soft graviton theorems in higher even dimensions, which is well established in 4 dimensions. And we did so in linearized gravity and in even dimensions. Soft theorems are known to exist in all dimensions, while supertranslations have been claimed to be absent in higher dimensions. And this is unsatisfactory due to the soft theorem and asymptotic symmetry correspondence. The absence of supertranslations is linked to using stronger boundary conditions in R. What we did to resolve this discrepancy was to relax the fall-offs in R and impose some fall-offs in U. And this allowed for a well-defined charge for supertranslations in higher dimensions, which also gave the correct soft graviton theorem. Some future directions. This analysis needs to be extended to, it's not clear how to extend it to non-linear regime, that is full Einstein-Hilbert action, and how to extend it to odd dimensions. And another thing one could try to do is to, instead of imposing these U fall-offs, one could try to add some counter terms, do holographic renormalization in asymptotically flat spacetimes, which is not trivial, and get finite charges. Another issue is to do a complete analysis for superrotations in higher dimensions, because they are linked to subleading soft graviton theorems, and and they also exist in arbitrary dimensions. So there should be some superrotation kind of symmetry in higher dimensions, and there is a straightforward generalization would be to say that superrotations in higher dimensions are just the diffeomorphisms on SD-2 sphere. And finally, it would be very interesting to study the higher dimensional Christodoulou-Kleinerman spaces. What are the conditions that we get, and whether these U fall-offs come out of those. Thank you.
Thank you. Thank you, Ankit, for this talk. So we have a question from Andrea, or was it the previous question?
No, it's a new one. So maybe hi. So one thing that I didn't understood. So how do you cure the divergence in R by imposing boundary conditions in U? So I mean, your charge, what are you using? Because if you are using the Barnish-Brand methods to determine the surface charge, I think be also divergence in R, right?
So I can show you actually the expression. So this is the pre-symplectic potential current, as you know. And when you try to find the symplectic form, you have to integrate over a constant time slice. So we basically do an integration by parts, and it turns out that the divergent part, there is a finite contribution and there's a divergent contribution, and the divergent contribution can be just, that goes away once you impose these U fall-offs.
Okay, but it's because you are integrating on a Cauchy surface here.
Yeah, exactly. Yeah.
Ah, okay, that's the point. Okay, thanks.
Another question.
Right, R is T minus U, and then.
Okay.
Yes. Do you have a good reason to believe that it is easy to extend the Christodoulou-Kleinerman in higher dimensions?
No, I don't. I think it will be very difficult. I don't think it's easy. I'm just saying that if it is done, then most likely you will get back these U fall-offs that we have. You will also get much more, but at the linearized level, at least you will get these U fall-offs.
All right.
Yeah, I don't know how easy or difficult it would be to generalize.
Well, at least the four-dimensional case is long.
Yeah, exactly. So they have a used book, and it's there.
Thank you.
Yeah.
Gaston?
Yes, hello, thank you for the. I have a question about what is known about superrotation. We know in 4 dimensions that superrotation, either you can consider the diffeomorphism on the 2 sphere or also some kind of conformal killing vector. So there are different choices you can do. So which are the speculations about this in a higher dimension? You expect also to have some conformal structure, at least in given dimensions, or just the people speculate with the idea of having a D-2 sphere and diffeomorphism? So on.
Yeah, I think it can only be the diffeomorphisms on D-2 sphere, because the other notion doesn't exist. Because, yeah,
well, you can consider some particular cases in which you have several torus or something like that, tori or something. At least with some certain topologies you can imagine.
Perhaps, but perhaps. But the most straightforward generalization is this diffeomorphisms on sphere. And actually, there was a paper where people actually did reverse engineer these super rotation charges, and they also interpreted it as like diffeomorphisms on D-2 sphere. But maybe.
Okay. And what's supposed to happen with what is known about the cohomology in the sense of how many is there some result for how many central extensions this such an algebra would support?
I have no idea.
Because now you have okay.
Yeah, I don't know.
Okay. Is there another question? If not, let's thank Ankit again for the nice talk.
Thank you.
And so next we have Romain. We're getting back on schedule. Incredible.
Okay, can you see my slide?
Yes.
Okay, very good. Okay, so first, I would like to thank you very much for organizing this very nice event, and also for giving me the opportunity to talk about my research. So in this presentation, I will discuss some recent advances concerning the quadrant representation of the BMS group in 4 dimensions. And this presentation is based on a paper which is in preparation in collaboration with Glenn, who was my PhD advisor. Okay, so first let me briefly draw the role of the quadrant representation in physics. So first, we know that at the quantum level of the theory, from Wigner theorem, if there is a symmetry of a quantum system, then it will act through some unitary representation on the Hilbert space of the theory. And so in this context, it's very interesting to try to classify the irreducible unitary representation of this symmetry group. And there exist some orbit methods that have been established by Kirillov and that relate precisely the quadrant orbits of the symmetry group with these unitary representations. So in this context, it is interesting to investigate the quadrant representation of the symmetry group and try to classify the orbits. So another motivation is actually at the classical level of the theory, where there is this momentum map construction that allows to obtain Noether charge for the theory. In this context, the quadrant vectors play a central role in the construction. So furthermore, sometimes the symmetry will act through the quadrant representation on the phase space of the theory. And as I will explain in a moment, this will be the case for three-dimensional gravity, where the solution space transforms in the quadrant representation of the asymptotic symmetry group. So let me briefly define what the quadrant representation is. So here I will start with a Lie group, G, and its associated Lie algebra. And then the adjoint representation is just a representation that is acting on the Lie algebra. And for the group, it is defined as follows. So you have an element here on the group in G, and it is acting on an element X in the Lie algebra in the following way. So basically, you take the exponentiation of X to obtain an element in the group. Then you perform the following operation in J. And finally, you take the differentiation to obtain again an element in the algebra. So similarly, you can obtain the adjoint representation of the algebra by just taking the differentiation of the adjoint representation of the group. And what you get is just the Lie brackets of the vectors in the Lie algebra. So now you can also consider the dual of the Lie algebra that I will write G star. And the quadrant representation will be a representation that acts on this space, on G star.
There's a question from Gaston.
Yes.
Was it the previous question from last time, I think?
Ah, okay.
Okay, sorry.
So to construct this quadrant representation, I need a map which is called the pairing, and that associates to one element of the dual and one element of the Lie algebra a real number. And then the quadrant representation will be defined as the dual of the adjoint representation. So it will be defined in the following sense. Here, you have your quadrant representation of the group, which acts on element P in the dual of the Lie algebra. And so it's defined as the dual of the adjoint representation of the group through this pairing map in the following way. So this defines univocally the quadrant representation of the group. And similarly, you can define the quadrant representation of the algebra as the dual of the adjoint representation of the algebra through this pairing map. So you see that all what you need to construct this quadrant representation is first to know what the adjoint representation is, and also you need this pairing map. So we will see some precise examples of that later. So let me now focus on gravity in 3 dimensions, and I will consider the case of asymptotically IDS3 space-time with Brown-Eno boundary conditions. So in this case, the solution space takes the following form. So the metric is parameterized by 2 functions, L plus and L minus. So one is chiral and the other is anti-chiral. And I will use here the coordinates x plus and x minus, which are the light cone coordinates on the cylinder. And so when you perform the analysis, you can show that the asymptotic symmetry algebra, preserving this boundary condition, is given by the conformal algebra in 2 dimensions. And it's the double copy of the width algebra, which is parameterized by 2 functions, y plus and y minus. So now for this asymptotic symmetry algebra, you can define a pairing in the following way. So you have one entry for the element of the algebra. So these y plus and y minus are parameterizing your asymptotic symmetry algebra. And the other entry here is for the elements of the dual of the algebra. And these functions are precisely those appearing here in the solution space. And then the pairing is just the following combinations, which actually correspond to the gravitational charge of the theory for these boundary conditions. And now from an explicit computations, you can compute the variation of the solution space. So here I wrote the infinitesimal variation of this solution space under the asymptotic symmetry algebra. And so here you recognize this Churchian derivative that involve the Brown-Hainaut central charge. And then what you can show is that this variation of the solution space precisely correspond to the coadjoint representation of the double copy of the Virasoro algebra with a fixed central charge. So this result is in agreement with the ADS-CFT, in the sense that we know from, so that in a CFT, the stress energy tensor will transform in the coadjoint representation of the algebra. So you can show that when you look at the finite transformation of the solution space, they also precisely correspond to the coadjoint representation of the asymptotic symmetry group instead of the algebra. So you have a similar discussion for asymptotically flat spacetime in 3 dimensions. So here you have this asymptotically flat metric written in Bondi gauge, and again parameterized by 2 functions. And the asymptotic symmetry group is in this case is given by the BMS3 group, which is parameterized by the super rotations and the super translations. Again, you can construct a pairing for this asymptotic symmetry algebra. And it corresponds again to the gravitational charge of the theory. So now when you look at the infinitesimal transformation of the solution space under this asymptotic symmetry algebra, you will find that it corresponds again to the coadjoint representation of the centrally extending BMS3 algebra with the following central charge. So in summary, what we have seen is that in 3-dimensional gravity, the solution space of the theory transforms in the coadjoint representation of the algebra or the group, depending on if you are looking at the infinitesimal transformation or the finite transformation. So these were known results. So now the natural question that we can ask, is it true for the case of 4-dimensional gravity in asymptotically flat spacetime? So does the solution space transform in the coadjoint representation? So in 4D gravity, the transformation of the solution space is more transparent in the Newman-Penrose formalism. So here we will work in asymptotically flat spacetime in the definition of Newman-Inti that involves this formalism. And then we will construct the coadjoint representation explicitly for BMS4, and that will allow us to identify the patterns of the coadjoint representation in the transformation of the solution space. So this is the plan for the remaining of the talk. So here is the definition of asymptotically flat spacetime given by Newman and Inti. And here I will work in these coordinates. So U is a kind of retarded time coordinates that label null hypersurfaces in your spacetime. R is a radial coordinates, which is an affine parameters along the null geodesics generating these null hypersurfaces in the spacetime. And psi bar correspond to the stereographic coordinates on the celestial sphere. So here, these boundary conditions for asymptotically flat spacetime are given in the second order metric formalism. But you can translate them easily into the first order Newman-Penrose formalism in the following way. So here you just have to express your metric in terms of null tetrad. You have to recast the spin coefficients in these lowercase Greek letters. And the components of the Weil tensor will be expressed as these uppercase size letters. Okay, then you can solve the equations of motion in this formalism. And what you find is the following solution space. In particular, you recover the peeling theorem for the expansion of the Weil tensor. The asymptotic shear will be defined here as the expansion of the shear, at the leading term of the expansion of the shear. You will also have some constraints in the coefficients appearing in this expansion. And finally, you will have this Hertz operator, which plays an important role in the Newman-Penrose formalism, and that appears naturally here in the expansions of the element of your solution. Okay, so in summary, the solution space in four-dimensional gravity in asymptotically flat spacetime is parameterized by the following functions. So these are functions of u, psi, and psi bar, which are the boundary coordinates. And here I translated these functions in terms of maybe in the bracket here, in terms of the function that appear in the metric formalism that maybe you are more familiar with. So it's parameterized by the angular momentum, psi 01, the mass, which is the real part of psi 02, the asymptotic shear, sigma 0, and finally you also need an infinite towers of subleading term, psi 0, which appears in this expansion of psi 0 here to specify your solution. And so these functions that parameterize your solution space are constrained through some time evolution equations. So this equation will constrain the time evolution of the angular momentum. This one will constrain the evolution of the mass. And finally, you have an infinite tower of time evolution constraining all these subleading orders which parameterize your solution. So in summary, to specify completely the characteristic initial value problem, you have to give the following data. You have to give explicitly this angular momentum at a fixed time, and also the mass and this infinite tower of subleading at a given time u0. And to specify completely your solution, you also have to provide this asymptotic shear function, but this time on the wall boundary, because sigma 0 is not constrained by a time evolution equation. So now the asymptotic symmetry algebra that will preserve the boundary conditions will be given by the extended BMS4 algebra. And it's given by the semi-direct product between the super-rotations that are parameterized by these holomorphic and anti-holomorphic function y and y bar, and the super-translations here, which are parameterized by these t functions. And so these functions satisfy the following commutation relations, which are precisely those defining the extended BMS4 algebra. So now by an explicit computation, you can find the transformation of the solution space under this extended BMS4 transformation. So here I just wrote the infinitesimal variation of the solution space. So here you have the variation of the angular momentum, the variation of the mass, the variation of the asymptotic shear, and finally here, the variation of all these towers of subleading terms that appears in your solution space. So here I just wrote the leading term variation. So now the question that we addressed is where is the coadjoint representation in the transformation of this solution space? So to answer precisely to this question, we need to construct explicitly the Coadjoint representation of the BMS group in 4 dimensions. And we will construct this representation on a 2 surface S, which can be seen as a section of null infinity square plus. So why do we do that? Is because basically the algebra here can be expressed very naturally on this this section of square plus, because it's in terms of functions that are that depends only on psi and psi bar. And we will endow this 2 surface with 2-dimensional conformal metric, which can be seen as the induced metric on the space-time boundary. So in our analysis, we will keep this conformal factor P generic. But if you want, you can specify the topology of this 2-dimensional surface and also the value of the conformal factor depending on the particular case in which you are interested. So for example, global or extended BMS. So now I will consider the following transformation on the conformal factor of the metric, which are called extended conformal transformations. And these transformations are composed of 2 types of transformations. First, you have the conformal coordinate transformations that induce some Jacobians in the transformation of this P. And you have this complex virus scaling here, because here is a complex function that is involved in this transformation. And then, so this transformation on P will, of course, involve the analog transformation, induce the analog transformation on the boundary metric. Okay, so now to describe the Coadjoint representation, we have 2 equivalent points of view. The first point of view is in terms of conformal fields. So maybe this point of view will be more useful for people working in CFT. And in this case, we consider some fields on these 2 surfaces, which transform in the following way under these extended conformal transformations. Okay, so these fields transform with Weil weights here, lambda and lambda bar, and with conformal dimensions h and h bar. So another point of view, which is maybe more useful for people working on solution space in GR, is this weighted scalars point of view, where here we are considering scalars with certain weights under, again, this extended conformal transformation, and they will have some conformal weights and spin weights. So these 2 points of view are actually completely equivalent and can be related through the following mapping here. So basically, if you start with a conformal field description, you can contract your conformal field with some well-choose power of P and P bar, so that at the end you obtain the associated weighted scalar. And so through this mapping, the weights of the conformal field point of view are related to those of the weighted scalar point of view through the following formula. So here in this presentation, since I want to identify the coadjoint representation in the transformation of the solution space of GR, I will only focus on this point of view of weighted scalar. But you have to keep in mind that all the results can also be stated in terms of these conformal fields. And in the article, we will display both points of view. So now here are the ingredients that you need to construct the coadjoint representation. So we will need a derivative operator D, which is related to the ETS operator that I introduced earlier and that appears naturally in the Newman-Penrose formalism. And so this D operator will act on these weighted scalar here. But in the conformal fields point of view, you can show that it actually corresponds to the Weil covariant derivative on the 2 surfaces. And so these operators allows us to make all our structure, all our construction Weil covariant. So now the elements of the BMS4 algebra, which are these parameterized by D functions that I introduced before, so the super rotations and the super translations, and also the elements of the dual of the BMS algebra, BMS star, which are here parameterized by these equivalent class of J, which are called super angular momenta, and these P, which are just the super momenta. And so here, these equivalent class of super angular momenta are defined in the following way, through the following equivalence relations. So the different objects that we introduce here to construct this quadrant representation have some weights that are displayed in these tabulars. So here it's it's the weight in terms of the weighted scalar point of view, but I have also displayed here the weight in terms of the conformal fields point of view. So now for this asymptotic symmetry algebra BMS4, you can construct a pairing in the following way. So this expression is very similar to the one that we consider in three-dimensional gravity. And in particular, so here you have an entry for the element of the algebra BMS4, and you have another entry for the element of the dual of the BMS4 algebra. And what you can show is that this pairing is non-degenerate. And this is the case because you are considering equivalent class of super angular momenta. So this is why I'm considering equivalent class and not just the J themselves. Okay, so now that you have the commutation relations for the BMS algebra and that you have a definition of a pairing here, you can actually construct explicitly the Coadjoint representation of the BMS4 algebra. And so this representation will act on the dual of my algebra, so on these elements of BMS4 star. And they are given by the following expressions.
So we have a question from Charles.
Yes.
Hi, Romain. Sorry.
Yes.
So is the pairing invariant under the transformation you've displayed?
So this pairing has some properties. Yeah, so it's invariant first under Weil because all our structure is invariant under this Weil scaling. But it's also, we have chosen the weights of the different ingredients in our coadjoint representation so that this pairing is actually invariant. So these weights here are well chosen so that under this kind of transformation, this pairing will remain invariant.
And under the equivalence class transformation?
Yeah, so actually you can, if you want, when you replace J by J plus this total derivative, we made the assumption that here total derivative can be thrown away. And so you can integrate by part, and here, so it will hit on the Y and Y bar. And since they are conformal killing vector, you will just get 0. So this pairing is well defined for these equivalent classes.
Okay, thank you.
So here is the quadrant representation of the BMS4 algebra. And now we want to identify the patterns of this representation in the transformation of the solution space that I introduced before. So here you can see that in the transformation of the angular momentum, you have some patterns of the quadrant representation appearing naturally if you make the following identification. Furthermore, in the transformation of the mass, you see that you also have some patterns of the quadrant representation that appear. So what we have done here is to identify precisely the patterns of the quadrant representation of BMS4 in the transformation of the solution space. So let me mention that this also works at the level of finite transformation. So if you look at the finite transformation of the solution space under BMS4 transformation, they will exhibit some patterns of the quadrant representation of the group this time instead of the algebra. So as we can see here, the quadrant sector only capture one part of the transformation in the solution space. So there are two other sectors to obtain the full 4D gravity transformation. And there is this sector of asymptotic shear here that is not controlled by the Coadjoint representation, and that basically contain information about the gravitational waves as a theory. And there is all this tower of subleading terms that is not captured by our construction. So to obtain the full gravity, you have to couple these three sectors together. Okay, so let me conclude by summarizing the results and giving some perspective for the future. First, what we have reviewed is that the solution space of three-dimensional gravity transforms in the Coadjoint representation of the group or the algebra, depending on if you are looking at the finite or the infinitesimal transformation. And furthermore, we have seen that in the case of 4D gravity, the solution space was transforming in a more complicated way. But then what we have done is to construct explicitly the Coadjoint representation for BMS4, and we have managed to identify the patterns of the Coadjoint representation in the transformation of this solution space. And in particular, we've seen that to obtain the full 4-dimensional gravity, we need to couple this Coadjoint sector, which is described by the Coadjoint representation, with the asymptotic shear and also with these subleading, this infinite tower of subleading terms. So this work offers some perspective for the future. First, it will be interesting to extend these results that we have obtained here on a section of Scribe Plus to the whole space-time boundary, Scribe Plus. And actually, we have already some results going into this direction. Another direction that will be nice to investigate is to construct some field theories that exhibits the BMS4 symmetries as global symmetries. And this can be done using this geometric action construction that just required the Coadjoint representation. And this construction was very successful for three-dimensional gravity. So we hope that it will also be interesting in the case of 4D gravity. And finally, it will be interesting to relate this Coadjoint representation with the recent investigation on the celestial sphere CFT. Okay, so I will stop here. So thank you very much for your attention.
Thanks a lot, Romain, for this nice talk. So we have several questions. One from Ali was first to raise a hand.
Yes. Oh, sorry. What is the motivation for this identification of the J's? What's the physical motivation for that?
So the motivation that we have comes from 3D gravity, where we know that all the solution space transforms in the Coadjoint representation. And you have some interesting things for that. For example, you have this classification of Coadjoint orbits that I mentioned at the beginning of the talk. And you also have this geometric action construction. And in the case, for example, of 3D gravity, when you use this geometric action construction, which is based on the Coadjoint representation, you can actually show that it reproduces the Hamiltonian reduction of Hainaut-Coussart. So this produced some nice results in this direction. And we hope to be able to reproduce these results in 4 dimensions. So in a sense, that will allow us to isolate one interesting sector in 4D gravity that is very similar to the sector of 3D gravity, and to have some control of it. And then at second stage, to couple this sector with the other sector of gravitational waves and the subleading terms that I mentioned. So these are my main motivation, I would say.
Yeah, I agree with the motivation, but what is the reason to identify two different, I mean, if I understood correctly, you identify two different angular momenta, right?
So
here, two different solutions.
So J and J bar, you are talking, or?
Yes,
So
Jay.
these are just the two components for the angular momentum. So you will have metric and phi and theta. So these are just the components of the superangular momentum. So if you want, these are the expressions that appear in the gravitational charge.
If I may.
Here actually you have some despairing, reproduce some parts of the gravitational charge in 4 dimensions. But of course you have to add the other sectors to obtain the full 4D charge.
Okay, so the question of Charles.
I don't know how to wave, but I have a related question. Hi guys.
Hey, pleasure.
Hey.
Pleasure.
But I don't know how to wave. This is the first time I'm using.
You can raise your hand. You have to click on the raise hand somewhere in the. You have to find
yeah, I was looking for that, but I haven't seen it.
Yeah, you have to click on
You're
participants.
on my list. I will just go keep the chronal order. So Charles.
Yeah, sure. Hi again. I was just wondering if you had any result. I mean, do you know the other sectors? They also transform in a representation, I guess. Do you have any insight about which representation it is?
Well, so the representation at the level of the solution space is well controlled. For example, we know that we have some Schwarzschild derivative appearing for the superrotations and so on. But I have I don't know if there is a representation, if we have to talk in terms of representation, because it's non-linear actually. So I don't know if we have to think about representation or just action of the BMS group on the solution space. So it's more an action that involves some patterns of the quadrant representation.
Okay. Thank you.
Was Mark?
Yes, hello.
Hello.
So you mentioned the orbit. Can you say more about the structure of the orbits of the coadjoint representation in 4 dimensions?
So that's one. So that's a point that I didn't mention, but actually that's something that we would like to investigate. So we don't have any results for the moment in this direction, but I agree that it's a very good question, and this is in our plan to investigate that. And we think that our construction could allow us to maybe try to classify these coadjoint orbits in the 4-dimensional case.
But could you see, for instance, what you call the other sector, or some improved, by some improved redefinition as parametrizing the orbits, the other variables, or?
So it may be that actually this, for example, this sigma 0 it's always turned on by the super translation, and so it may be one of the parameter involved in the description of the orbits, but it's not clear at this stage for me which will be the good parameter for the different orbits. But yeah, that's a very good question.
Fabio?
Hi, thanks for the very nice talk. So if you start with some type D solution in the Petrov classification, like so I'm thinking about black holes. So what happens with this? All the shear is 0 or something like that?
So here, for example, what I can say for the transformation of the shear is that if you act with super translations, it will always turn on the shear. Even if you start from a shear which is 0, the super translation will always turn on this shear. So you cannot keep it at 0 under a super translation. So that's why we cannot actually really isolate a subsector of the solution space, but more some patterns in the transformation of the solution space. We cannot isolate, if you want, a subsector in the solution space that transforms in itself in the quadrant representation. It will couple to other things. And for example, with this asymptotic shear.
Okay. Blasha?
Yes, thanks. So, wait, video, hi. So, related to this notion of gauge invariance for angular momentum that Ali was pointing out, I think your statement was that the gauge transformations do not change the charges.
So if you change angular momentum aspect by a gauge transformation, you don't actually change the physics of what you're looking at. But you also mentioned that the charge, the pairing that you wrote, is only part of the surface charge. So is this gauge invariance of the angular momentum consistent with the rest of the charge? Like if you change your J by a DL, as you write on your slide, do you also leave the rest of the surface charge invariant?
I would not expect so. I would have precisely to look at the charge, but I think there will be some CAB which are non-constrained by this operator. So I expect that this cell will not be zero. And actually, the fact that here we have this invariance is very related to the fact that we are considering holomorphic and anti-holomorphic functions. But for example, with the diffs2 super rotation, we will not have this kind of feature.
With diffs2, no, but with sdiff2, with area preserving diffeomorphisms, you will.
Yeah, sure. Yeah.
Okay.
Yannick?
Yeah. Hello. So I have a naive question. So charges, the BMS charges, they are elements in the dual of the BMS group, right? Because you take a Lie algebra element of BMS, you pair them, and you get a number. And so when you have no fluxes, these BMS charges, they have to be BMS invariant. So therefore, they would be in the representation of this quadrant. They will be in this quadrant representation. So is this? So my first question is: do you get just that, like that? Are you finding again charges here? And can we think? Is it correct to think of this work as sort of rederiving the BMS charges, but from representation perspective?
So yeah, that's a good point of view. So actually here, the pairing of BMS4. So we saw that in BMS3, for example, or in ADS3, this pairing corresponded precisely to the gravitational charge, to the full gravitational charge. But in the 4-dimensional case, the charge here, this is only a subsector of 4D gravity. And this will basically correspond to the charge associated with this subsector. So this pairing corresponds to the gravitational charge, but with assumption on the asymptotic shear, and that's all. Yeah. So if you turn off basically the asymptotic shear, you recover this combination for the BMS charge.
So questions keep coming. So at some point we will stop, but let's Marius.
Yes, this is a question about ADS, because since you have worked also on ADS, maybe you can make a comment. I expect that in ADS you have a decoupling of this. The three sectors that you have will appear in a single sector, right?
So yeah.
So my question is therefore: do you have an idea of how this could be seen at the level of representations?
So my guess, so I've not looked precisely at ADS, but for example, if you take ADS with Dirichlet boundary conditions, what will compose your solution space is made of this holographic stress energy tensor. And we know from ADS CFT that it will transform in the quadrant representation of the CFT. So I expect that there, for Dirichlet boundary condition at least, the solution space will transform actually in the quadrant representation of the conformal group on the boundary. So that's my guess. It's more actually involved for asymptotically flat spacetime because of this asymptotic shear, but that we don't have in ADS because it's constrained, as we know very well, by the boundary metric, or it's zero for Dirichlet boundary condition. Yeah.
Right. Thanks.
And then there will be a last question from Andrea. Actually, I'm going to ask a question also. So Andrea, maybe first.
Okay, so but then you said that the charges that you showed before, so you can put them in correspondence with the part of BMS charges, right?
Yes.
But so what you are missing is the quadratic part inside the BMS charges. What? So you have only a conservative part. So your charges are conserved on Scry.
Yes, absolutely.
Precisely, yeah. So what we are missing precisely is the asymptotic shear in this. So here we have only the quadrant subsector, but we are missing the term involving the asymptotic shear. and which are responsible of the Bondi news. So when you take the time derivative of the asymptotic shear, you get the Bondi news. And this is what is responsible for the non-conservation of the BMS4 charge. So here, the Coadjoint sector of 4D gravity is very similar to 3D gravity, actually. So that the charges are conserved, and you have all the interesting characteristic of 3D gravity.
But in this sense, are your charges, so they look like charges at space-like infinity in a sense. So it seems that you are looking, so is it correct to say that you are looking at the action of the Coadjoint action on stationary solutions of the field equations? So if you just restrict yourself to look at the space of a stationary solution of your field equations, you don't have a problem of radiation. And is everything controlled by Coadjoint action?
So it will be true if the asymptotic shear will not transform under supertranslation. So basically, if you start with asymptotic shear 0, then you will get something which is non-zero. And this will modify, probably, I have to check precisely, but the expression of the charge here, because of this non-zero asymptotic shear. But I think they will still remain conserved because they will be non-use. And but you can actually turn on, I think, the news with the super rotations. So you have to be very careful with that. But the point here is that we cannot really isolate a subsector that transform in the Coadjoint representation, and that is completely described by this. It's just some patterns in the transformation of the solution space.
Okay, thanks.
Okay, so I will ask the last question. So for the case of DFS1, so for the Coadjoint orbits relevant for the 3D case, one can express the charges, the super rotation charges, as some stress energy tensor over Liouville theory in terms of a chiral boson, and it's a useful decomposition of the charge, which is related to also to the construction of a theory. So is there a way were you able to already find to decompose the charge here for this case, the 4D case, in terms of some stress energy tensor, in terms of more fundamental fields like chiral bosons?
So I would say that we have, in a sense, the analog of the construction of ADS, but it would be actually interesting to. So that's actually part of the project on which we are working now, is to extend all these results from the two surface through the whole space-time boundary. And in this term, we have naturally some Carolian structure that appears. For example, this Weil derivative operator, which is useful to describe the Coadjoint representation, has a very nice interpretation in terms of Carolian structure on the boundary. So it seems that we can have the analog of that, but it will involve some Carolian geometry on the boundary. And so we hope reproducing this three-dimensional action living on the boundary, which will be the analog of this Liouville chiral boson in 3D. Yeah, that's part of our goal.
Okay, thank you.
Thank you.
I think we should stop here to have time for lunch. So I would like to thank all the speakers today. Well, let's thank Romain especially. And so we have 1 hour for lunch break, and we resume at 2. Thanks to all. Actually, Romain, another question actually, but
I can stay.
Ask you here. So this operator, the Weil conformal operator, is it the same as the one defined by Campiglia in his last paper? He also was defining some Weil type algebra that was actually useful.
Yeah, I would say that here this operator is more, it's motivated by the Weil invariance of the structure, while in the case of Campiglia construction, I think it was for more in the DFS2 transformations. So maybe they are related,
Yeah,
but
at the end, there's only one vice structure, so they should be related.
Yeah, they should. Maybe I could have a look to that. I cannot answer precisely actually, but maybe that's actually an interesting question. Yeah.
Okay, so we'll close the session.
Okay.
Thanks.
Thanks.